I have a short presentation today and what was going to be a live demo, but is now going to be a short video because it turns out it was going to take a while to record to download a large language model, and nobody wanted to sit around for 10 minutes watching a download progress bar happen. So I've got a video that stitches that together and makes that a little bit faster. So to start off with, my name is Michael Hall. I'm a developer evangelist at ARM. We are the company who designs ARM CPUs and the ARM instruction set. I'm here today to talk mostly about generative AI and how you can run it on those CPUs and things that are being done to make that more efficient and more effective for you so that you don't need a big, powerful cluster or set of GPUs in order to do that. So start out with a little bit of background. AI has come a long way over the past half a century since it got started. Back at the beginning in the 1970s, it was very rules-based. So a developer had to explicitly say what to look for, what that means, and how to respond to that, which worked for a very limited set of circumstances. If it was a very controlled environment, that was good enough, but it didn't have the flexibility to be able to apply that to real-world examples. That started to change in the 1980s and 1990s when machine learning really came on board. And that allowed us to let the computers start to learn for themselves what to look for and what meanings those things will have. So neural networks came around, a whole bunch of math got involved in that so that the computers themselves could start to recognize those patterns for us. That let us do things like some basic object detection and image recognition, a little bit of natural language processing as well. And then deep learning neural networks came on that added layers and layers of neural networks together to improve those even more. So that's led us to almost where we are today. But I wanted to share this comic because I find this very funny. This was an XKCD comic from 2014, making fun of the fact that it was really simple to use GPS to determine if somebody was in a national park or not, but described the task of identifying whether or not a photograph has a bird in it as a nearly impossible task that would take 5 years of research. Now, of course, 10 years later, that is such a trivial example that it's just kind of expected for any kind of photo application anymore. You can do this on tiny little microcontrollers that cost you $5. But it's interesting that something that was once considered a virtually impossible task for computers to do has now become really a trivial task for those computers to do. And that brings us to kind of the next big evolution in AI, which was the introduction of generative AI. That's really taken off now and is changing not only what we think about AI doing, but how we do it and where we do it. It's important to think about all of the different places where AI can run. The cloud is obviously a very important role in AI, both for development and deployment, but it's not the only role. We've got compute power on the edge, on on-premise servers, on mobile phones, even on embedded devices, and all of those are capable of running AI workloads to different degrees, and even generative AI workloads. Some of the benefits of running them on-prem or on your own devices. Privacy is becoming a growing concern with AI. When you control your AI model and where it runs, you get to control what information is going into it and what information is coming out of it. Energy efficiency is also a growing concern. We've all heard stories about how expensive it is for OpenAI to run ChatGPT and how much energy they're burning through for that. If you're running your models on your own servers, your own hardware, or even your own devices, you can control that energy usage as well. It's really going to be up to the developer, though, where their application runs. And the developers have to be mindful of what the resource constraints are, both for their use cases and where they want it to run. In the cloud, you've got a whole bunch more resources. You can do a lot more with larger models. But if you're running it on the edge or on devices, you have to be more mindful about things like storage space, how much memory you have, in a lot of cases, even your energy usage, because you might be running on something that's battery powered. And so the type of application you're developing is to some extent going to determine where that can run and what your options there. But it's important to be mindful that you do have all of these different options and what those might mean for you. Like I said, Gen AI has really kind of taken over with ChatGPT coming out 4 years ago now or something. And that one's really still in the show. But there are a bunch of other models that you can, a bunch of other different things that you can do with generative AI. We've seen image generation with Stable Diffusion and DALL-E, a lot of those out there now. But even things like computer vision, which has not been quite as glamorous, but when you think about it, that's playing an important role in all of the autonomous vehicles that are coming out there now. Being able to not only recognize what they're seeing, but being able to predict what that might mean in the next few seconds. So detecting that there's a car or a pedestrian, but also what direction they're moving, how fast they're moving, and be able to predict where they're going to be so that you can sort of avoid them or brake or whatever it is that you need to do. Even audio processing is benefited greatly from these new language models, being able to clean up audio, being able to separate foreground audio from background audio, things that used to be really hard tasks for audio engineers to do. AI is now able to do to a greater and greater extent. So there's all these different types of large language models out there now, and even combinations of them where you can have multiple types of models in one. Most of these are dominated by the transformer architecture, which is what powered ChatGPT. But another evolution that is not quite as well known is that models are shrinking. ChatGPT, the latest ChatGPT, is up to almost 2 trillion models and takes up some hundreds of gigabytes of memory, terabytes of memory probably now. But models are also getting smaller, and a lot of work is going into that. Different things that can be done. You can do compression, where you just squeeze the model down to smaller sizes. But the more interesting one, for me anyway, is quantization, where instead of dealing with 32-bit floating points for all of your parameters, you can start to cut off some of those less significant parts of the numbers and make the size of the data that you're working with quite a bit smaller. There's always a trade-off with this between accuracy and efficiency. The fewer parameters you have, the smaller your parameter sizes are, the less accurate it's going to be, but there are ways that you can work around that. So now we've got models from like Llama or for Gemma that are 4 gigabytes, 2 gigabytes in size, which means that they can run on embedded devices or smartphones, and you don't even need a full server anymore. And frameworks like Llama CPP have 20 or more compression techniques that it uses at different stages of processing to be able to squeeze even more performance out of these models. So even though the big large language models, the ChatGPTs of the world, keep getting bigger and bigger, there's a big push happening right now to make those small models smaller and smaller. And that not only makes it to where they can run in less memory usage, it means that they don't need quite as much compute power either. So you don't need a big powerful GPU to run these models anymore. You can do it directly on the CPU. Which is good because ARM CPUs are everywhere. We are the only platform that you will find, from sensors through desktops, automotive, edge devices, even up in the cloud now. And it's the same instruction sets everywhere, which means that all of the software that's being ported to them and the optimizations that are going into them are available on all of these different platforms. And we've been doing this for a while. ARM as a company has been around since the 1980s. We were in the very first generations of cell phones, so from smartphones all the way up, we've been there. Back in 2015, just after that XKCD comic I shared earlier, we introduced our first set of optimization instructions called Neon. These are SIMD instructions. That's single instruction, multiple data. These are instructions that let you do the same operation on multiple points of memory at the same time. So if you had like 20 different numbers that you wanted to multiply all together, instead of doing them one at a time in 20 different steps, these instructions let you gather them all up together and say, run this one multiplication instruction across all of those. And it can do that in one CPU cycle instead of 20 CPU cycles. So we had a whole bunch of those that were introduced in ARM v8 back in 2015. We expanded that with SVE and SVE2. That stands for Scalable Vector Extensions. Whereas Neon, there was a fixed length of those vectors that you could use. With SVE, each silicon manufacturer can decide how big they want that vector space to be. So depending on what their use cases is, they can go as low as, I think it's 256 bits, or as high as 2048 bits. So for the top of the line server CPUs, they might want all the extra bandwidth that they can get for that processing. But from an application perspective, it's completely opaque to you. You just write your code to use these, and it'll use as much space as that silicon has to offer. And our next big improvement on that is SME, that's Scalable Matrix Extensions. And that takes the optimizations that we did for vector operations and extends that into matrix operations, which is hugely important for machine learning and AI, where you're doing quite a bit of work against matrices as well. So that came out just a couple years ago. And because of the life cycle to go from designing the instruction sets to getting it into silicon designs, getting that silicon actually being manufactured, and then finally into production in end devices is a years-long cycle. We're just now starting to see these ARM9 CPUs come out in some of the latest flagship cell phones, as well as some of the very latest server CPUs that are coming out. So those extensions are now available, and we continue to innovate there to provide more and more optimized instructions for ARM CPUs. So here's just a few examples of where you can find CPUs that do have those accelerated operations in them. Again, all of the flagship smartphones that are out there on the market, some of the leading cloud providers like AWS is using it. Graviton 3 has got ARM v8. Graviton 4 has got ARM v9. So it's got the newest ones in there as well. The Grace Hooper and the new Grace Blackwell chips from NVIDIA pair an NVIDIA graphics core with an ARM CPU that are also the ARM v9. And Alibaba's cloud's got that as well. And the cloud providers love it because energy usage is one of their biggest expenses. It's projected that by the end of this decade, 20% of the US energy grid is going to go towards powering data centers. And they're getting bottlenecked on that. They can't provide enough power to run the hardware. They can't provide enough power to cool the hardware. So when they saw us with these power efficient, high performance chips in cell phones, they really loved that idea and started working with us to expand those out to be server grade chips to power the cloud. So now AWS is on their 4th generation of Graviton cores. Microsoft just made their Cobalt CPUs generally available. Google's Axion they announced earlier this year. And again, I mentioned NVIDIA with Grace Hopper and Grace Blackwell as well. And these statistics are coming from those companies themselves. So Amazon saw a 60% improvement in energy efficiency by switching over to Graviton. Microsoft said they're seeing 40% more energy efficiency. Axion, again, 60%. And then NVIDIA's 25 times more power efficient than paired with an x86 chip. So they really love this. It's good for them. They pass the savings on to us so that we get slightly less expensive instances if we start using these. And they're better for the environment. They're not drawing as much power. They're not using as much water. That's good. That's a concern a lot of people have about generative AI, the cost of it on the environment. So switching over to ARM CPUs is a good way to help that as well. Yeah. Yeah. It's going to be a lot of the same instructions, depending on the NPU. The comparison might be a little bit different one way or the other. But it's going to operate like a CPU. It's going to be processing stuff in order, not out of order like a GPU would. But it does have those matrix multiplication extensions and things like that that an NPU would have. So you get a lot of the benefit of having a separate NPU just baked into the CPU core itself now. And one of the benefits of all of these optimizations, both in the model size, in the ARM hardware, and in the supporting libraries, is that you can run these large language models and generative AI now on your own servers. It doesn't really take that much. You can run this on like an extra large AWS instance and serve multiple simultaneous users against a chatbot. We do have a learning path here. If you want to try it out yourself, you can do that. It doesn't take very long. It's like 20 minutes end to end to do that, and costs you maybe $1 in AWS server credits. That's actually what the video is going to be on, that I'm going to show a little bit later. And if you want to try it out yourself in person, if you stop by our booth, which is here on the opposite corner of this building, we do have a live demo running there that you can try out as well. And like I said, some of these models now are 4 gigabytes or even 2 gigabytes in size, which means you can start putting them inside your mobile applications. You can run it entirely on a mobile phone, completely disconnected from the internet, and still get the kind of response times that you would experience by using ChatGPT, which is nice because now you can embed support into your application. You can even do really interesting things like using generative AI in a game itself, either generating dialogue, content, or even like the narrative of the game itself. Unity has a whole new library called Centis, which is using generative AI inside of their mobile games. So that is now all becoming possible, and we're going to start seeing a lot more of that, which is really cool. And if anybody wants to see it running on a phone, I've got it running here on my personal phone. If you want to come up after the talk and try it out, you can do that as well. So the size of your model is really going to be the main concern when you're thinking about where you want it to run. If you're using a really large language model because you want it to have really great conversational aspects, or you will have a lot of data that you want to train it on, if you're looking at like one of these 70 billion parameter models, that's going to be something that you're going to have to run in the cloud, just because the model's too big to fit into memory on anything smaller than that. But once you get down to like the 8 gigabyte threshold and lower, suddenly that opens up the possibility to run these on these mobile devices or embedded devices. Again, you lose a little bit of accuracy. It's not quite as good at conversation as the larger models are. But for things like support or some in-game narrative where you have kind of narrow constraints about what you want it to be doing, it becomes a really great option for you. Now, it wouldn't do us any good for us to have hardware everywhere if you couldn't use it. So ARM is really dedicated to making sure that whatever platform you're using, whatever form factor it's in, if it's got an ARM processor in it, we want to make sure that it also has the software that you want to be running. So we are fully committed to supporting software developers and making sure that you have a good experience with your software, with our software, with all of the stack in between it as well. So we're committed to bringing AI to the world's 20 million software developers and their billions and billions of users by focusing all the way up the stack from hardware up. And what that looks like is the fact that 40% of our engineers work on software projects. Even though we are a hardware company, we're a hardware IP company, almost half of our engineers are doing software work. We've been doing this for a combined 15 years across the board, and we have been involved in either producing ourselves or contributing to more than 1,200 open source and software projects. We do have our own GitHub organization with multiple repos there, so you can see our code. We're also heavily involved in open source projects like GCC, LLVM, PyTorch, TensorFlow, even the different languages like Java and Rust, we've got people involved in. We collaborate with over 50,000 companies across all of these different projects to make sure that the software that you're using, whatever that software is going to run well on ARM hardware. And that means you don't just, it's not just write once, run anywhere. It's also optimize once, run anywhere. Because those CPUs are the same across these devices and they use the same instruction sets and they operate the same way, optimizations that are being done for PyTorch in the cloud is also going to benefit you on the mobile phones and vice versa. Which means that, again, wherever your software is running, you get to benefit from whatever optimizations have gone into that software. It also means that whatever stack you're using, you get to keep using. We're not asking you to change language. We're not asking you to change frameworks. We're not even asking you to change models that you're using. You can continue using that and get all of the benefits that are going into it. Our newest contribution to this is called Kleidi. Kleidi is a set of accelerated libraries for machine learning and AI use cases. And we are working, getting ahead of myself there. We are working with upstream projects to define how this library looks and what operations it does, so that it is providing them exactly what it is that they want to get from us. So we're not just coming here saying, we did this all ourselves, start using it. We're working with these upstream projects to define what that looks like so that it fits exactly where they need it to fit. Again, it's going to go in under the hood. So if you're using something like PyTorch, you don't have to use Kleidi directly. PyTorch is going to use Kleidi, and you're going to get those benefits automatically. Kleidi AI itself is a collection of microkernels. And in the AI space, a microkernel is a set of instructions to perform a specific task. So something like doing a matrix multiplication on 8-bit integers. These microkernels are handcrafted by ARM engineers in assembly code and then wrapped in a C interface. So we know that if you call this API to do a matrix multiplication on an ARM v9 processor, it is going to use the most effective route to do that operation, using all the instructions that are available there, using the best use of memory, and all of that. Again, handwritten by experts, so you get a better performance than you would get out of what a compiler would automatically generate for you in that use case. And this is what's being integrated into these frameworks. So now, instead of using their own code to do this or relying on the compiler to produce it, they will call Kleidi AI's code directly and make sure that they get the top performance out of that they can. Kleidi is open source, so it is something that can be included into any application. It's a permissive license, so it can be included in open source and closed source frameworks, both. Again, we are working with the developer ecosystem to define what those microkernels are and how they work, so that they are exactly what those frameworks need. And in addition to just the code, we're producing documentation and other resources to help people learn how to use it and use it as effectively as possible. Just a couple of examples from recent integrations. When we integrated Kleidi AI into PyTorch, they saw a 12x increase in the token generation speed. So that took it from running 3 tokens per second, which is a little bit sluggish for an interactive chat AI, all the way up to 36 tokens per second, which is more than fast enough for a conversation to happen. Likewise, Executorch, which lets you run it on small mobile devices, saw a 20% improvement in the time to first token, just by integrating this Kleidi AI library. And again, as an application developer using these frameworks, there was nothing you have to do to see these performance improvements. You just get them automatically by using that framework. So we've got a few different learning paths that you can learn how to do this in your own applications. Whether it's running on Graviton with AWS, which is what we're demoing over at our booth this week, or running it on PyTorch, or using, again, Executorch on mobile phones. And you can see that happening on my phone as well. If you go to arm.com/learning or developer hub, you can get access to these and plenty more. We've got like 200 some odd learning paths now for different ARM technology and different use cases. So go check that out. And now we're going to try this video. See if you get audio from it. You do not. Anyone hear that? So that you can integrate it with your own application. We're going to use Llama CPP for this. So we're going to download that source code and build it on our server. Nope, that is not working. It uses oh, there it goes. Foundation for our chat bot. So this is one of those learning paths that I had run even faster on ARM servers, and then show you how to integrate it with your own application or source code. So to get started, we're going to go to AWS, and we're going to launch a new EC2 instance using Graviton 3 processors. We're going to look for the C7G instances. We're going to get either an extra large or a 2XL instance size. So first of all, go to launch a new instance. You're going to give your new instance a name. I just use LLM learning path. And for our examples, we're going to use Ubuntu as our operating system. So just select Ubuntu. It will default to 24.04. And then you just want to select the 64-bit ARM architecture for that. And it'll use the correct Ubuntu image for ARM. Next, we're going to choose our instance type. In this example, I'm going to use the C7G extra large, which has got 4 virtual CPUs and 8 gigs of RAM, which is more than enough for us. I'm also going to choose a key pair that I've already created to use for this example. And because we're not building a production server on this, just a simple SSH connection into the box is all we're going to need. And we're going to use about 8 gigabytes of space just for our models. So I'm going to increase our storage size to about 20 gigabytes. That way there's more than enough for the models and the operating system. Again, not a huge instance,
now we just have to review our settings.
4 virtual CPUs and 20 gigs of storage space.
This
Not
takes
a
only
big
a minute,
and then we can go into our instance page and grab that public IP address that we need to SSH into our box. So just copy that IP address, go over to your terminal. We're going to SSH in. Again, I already have a key pair here on my local machine that I'm going to use for this. And then, because the default user for Ubuntu instances on Amazon is Ubuntu, we're going to use Ubuntu at, and then that public IP address. So we just copy that in here, and that will get us connected to our new instance. Accept that fingerprint, and you're in. All right, now we're ready to get this going. First thing we're going to do with our new instance is make sure that it's up to date. So we're going to run apt update. We're also going to start installing some dependencies. The first dependency we're going to install is make, CMake, which are the build tools that we're going to be using for Llama CPP. So as soon as those are done, we will go ahead and grab the next set of packages, which is going to be GCC and G++. Those are our C and C++ compilers that we're going to need to compile that code.
And you really only need this
grab
if you're compiling
which
llama.cpp,
is
you
an
don't
Ubuntu
have to.
package that has a lot of programs and utilities that are useful for compiling binary applications. So again, just copy these 2 lines directly into your terminal. Let it go ahead and do that. And the next step after we have all of our dependencies is to get the source code for Llama CPP itself. It is an open source program and it's all available on GitHub, so we'll just git clone directly from there. And then as soon as we have that source code, we just cd into that new directory that Git created for us, and we run the make command, which will start the compiling process. Now, compiling does take a little while, so we're going to go ahead and speed through this video and get to the end of the compile stage. Once that's done compiling, you can test that it's all working by running llama-cli with the -h flag. And then you should see the output of the help information that tells you that everything's compiled right and we're ready to move on. Next, we're going to get the model and we're going to download that directly from Hugging Face using the Hugging Face CLI command line utility. It's a Python utility, so the first thing we're going to do is we're going to make sure that we have all the necessary Python packages installed to run a virtual environment. That'll let us install the Hugging Face CLI locally instead of system-wide. Our next step is to create that virtual environment in our Llama CPP folder and then activate it for our current terminal session. You'll see that little VN at the start of your prompt that tells you you're in the virtual environment. Now when we run pip install for this Hugging Face hub package, that's just going to install it locally for us. And this Hugging Face hub package includes the Hugging Face CLI utility that we're going to use to download our model. We're going to use the Llama 2 7B model from the bloke. This is a pre-quantized model, so it's been quantized down to 4-bit integers instead of 16 or 32-bit floating points, and that reduces the size from about 40 gigabytes down to just 4 gigabytes. The Hugging Face CLI will let us download directly from there and give us a copy of that in our local directory here. Now, this is a 4 gigabyte file, so if you're doing this over a slow internet connection, it might take a while. But if you're doing it over AWS, like I am, that's got a nice fast internet connection, and that download happens. But not always, because when I tried this last night, it was going to take like 10 minutes, even though it's the same size. This is a method of taking a large language model and reducing the size of the parameters in the model so that you can get it into a smaller space, and it'll run a lot faster. So instead of 32 bits per parameter, we're just going to use 4 bits per parameter. So once we have that model, we're going to go ahead and run our Llama CPP executable that we built using that model and give it an example prompt. For this, I'm just going to say building a visually appealing website can be done in 10 simple steps. That's going to be our prompt, and then we're going to let the LLM finish that prompt. So let's go ahead and run this. There are some things that we get in the output here that tell us about the environment we're running in. You can see that it's running really fast. It's created our first token right away, and the token generation rate is also pretty fast. In the initial output, we see some flags that it is using. So it's using the neon flag, which tells it that it not only knows about the neon extensions in the CPU, but it's able to take advantage of those. It also sees the SVE, or scalable vector extensions, in the CPU, so it can take advantage of, again, some additional extensions in the ARM architecture that are good for AI and machine learning processes. It also has the ARM FMA, which is floating point multiply and accumulate, and this matrix multiplication for 8-bit integers. So those 4 different extensions that are available in Graviton3 all serve to accelerate running AI and machine learning workloads on the CPU. And you can see this prompt took about 20 seconds to answer, but we can make. Right. I'm going to stop it there. There's more to this video. I do some requantization to take better advantage of the, to give a better data layout for running it on Graviton3 processors. There's more to this video. There's more to this learning path. But that kind of gives you the idea of what, how simple it is to get a model running. Also in this video, I'll show how to put up an OpenAI compatible interface around this so that you can just point something else to that API and use it. This video is available on our developer hub, so is the learning path that I was using to follow along with that there. So going back to our slides, like I said, we're very focused on software developers and making software developers' lives easier. We have been working for quite a long time on improving our own processors for these new workloads that are coming out as part of the AI revolution. And fortunately for us, we had already started down that road before Gen AI really exploded onto the scene and became much more demanding for that kind of thing. You can find those new chips and all of those optimizations across the board, from your mobile phones all the way up to your cloud providers. And you can find those integrations already starting into things like PyTorch and Executorch to take better advantage of those things. So if you want to learn more and you want to see it in action, you can, like I said, come up and see me after this to see it on my phone, or visit our booth on the other side of the building, and we can show you a live demo there, and you can get a really nice candy bar as long as they last, which are going fast. So if you haven't gotten one yet, I would encourage you to stop by today and not wait until tomorrow. Also, if you're a software developer, join our developer community. We've got almost 14,000 members now as part of our developer program. If you sign up for that, we will send you links to all of the resources that we have online. We'll get you an invite to join our community Discord, which has got 4,000 or so people in it, both ARM experts, ARM engineers, and people from other companies who are working on software or hardware projects themselves. We also are always looking for ambassadors. These are key members of our developer community who are out there promoting ARM technology and ARM hardware, doing things like running hackathons, doing webinars, teaching at universities even. We've got a whole program for supporting them, both with resources and with money for things like travel or to buy devices for the things that they're doing. And like I said, we've got 230 plus learning paths that cover all of the different ARM technology that's available and almost all of the different use cases you might think of to do with that. This is an open source project as well. It's all just markdown content. So if you have a project using ARM that you want to share with the ARM community, you can contribute a learning path to show people how to use that as well. Again, you can find that on arm.com/devhub. that is all up on Discord, or sorry, on the GitHub. All right, so that is the end of that. If anybody has any questions, I'd love to answer them for you.